when I say the word centroid, like I said, you can see that it seems like I'm saying center, but it's a little bit more than that, right? So when we say centroid, we're actually talking about the geometric center of a body, of a shape, of an area, of a volume, of a line, of anything. I'm just going to call it a body. And what geometric center means is that if you were to stand on the centroid and look in any direction, you would essentially see the same amount of volume in your line of sight. It doesn't matter which way you turn, you would always have the same amount of volume. So let me give you a quick example. Let's say we are looking at a circle. If I want to stand at some point inside this circle, and I want to make sure that wherever I look, I have the same amount of volume, where do you think I should stand?
The center, right?
Yeah, at the center of the circle. So if I were to stand somewhere in the circle where I can see the same amount of volume, it would be the center of my circle. And what that means is that it doesn't matter which way I turn, if my line of sight, right, if my line of sight is constricted, right, to these angles, then wherever I turn, I will always have the same volume inside this wedge formed by my line of sight. And that's essentially the definition of a centroid. Wherever you stand, right, you're going to see the same amount of volume. Now, when we're talking about centroids in this class, it's not enough to know that it's the center of a circle, for example. We also need to make sure that we know how to express the centroid in a coordinate system. Now, in statics, we're used to the Cartesian coordinate system, which we've already used several times. You may remember the Cartesian coordinate system is this x, y, and z space that we typically look at, or xy plane that we look at. What the Cartesian coordinate system tells us is that we can measure or locate points at any place, at any surface, at any body, by looking at them as measurements from coordinate axes. So in this case, if we're looking at our x and y axes, and let's say that our origin is somewhere away from the circle, if I were to say, well, this is a circle, and I were to ask you to give me the coordinates of the centroid, then you would essentially have to give me the x coordinate from the origin to the x location of the centroid. What that means is that you're essentially going to have to give me this coordinate, right, from the origin to this location. Likewise, you can give me the y coordinate of the centroid, again, relative to the origin. And what that means is that this centroid will have coordinates of x bar and y bar. Now here's your first bit of new information for this material, right? When we look at the coordinates of a centroid, we typically represent them with x bar, y bar, and z bar. Okay, so coordinates of the centroid, x bar, and y bar. Sometimes, and in many cases, your origin will be away from this point, which means that you need to know the distance between the origin and your shape, and then the distance between the edges of the shape and the centroid. So one example for circles, we're typically given a radius, or if we're not given a radius, we're typically given a diameter of a circle. And we can use this geometric information of the circle to find the location of the centroid. For example, if I were to tell you that the left edge of the circle, the leftmost edge of this circle, is located at points 2, 2. That means that the point and the leftmost edge of the circle is at coordinates 2, 2. And if I were to tell you that this circle has a radius of, let's just give it 2, a radius of 2, then what would the x and y coordinates of the centroid of the circle be? Can anybody figure out where those coordinates would be?
Is it 4, 2?
Yeah. So in the x direction, we know that the x coordinate of the left side of the circle is 2. And we know that from here to the center of the circle, we have a distance equal to the radius, which is 2, which means that the x coordinate of my centroid will be 4. Likewise, on that end, we know that the left coordinate, the y coordinate of the left point of the circle is 2. And we know that the leftmost point of the circle is already going to be aligned in the y direction with the centroid, which means that my coordinate will be 2. So for this particular circle, my centroid will be at coordinates 4, 2. In other words, my x and y bar will be equal to 4, 2. And I'm not giving you this example because we're going to be doing this a lot. I just want to make clear that understanding how coordinate systems work and understanding how we can locate these centroids based on these coordinate systems will be crucial for us to using the many equations that we're going to learn in this class. So we looked at a circle as an example. Let's try a different example. Let's look at a rectangle. So if I have a rectangle, typically for rectangles, we need to be given 2 dimensions to understand how this rectangle is located. Typically, we are given the base of the rectangle and the height of the rectangle. All right. So my first question would be, where, right, within this rectangle, where would the centroid be located?
So is it so in half of B and half of H?
Yeah, exactly. The centroid for this rectangle would actually be located at the center of the rectangle, the center of the horizontal direction, the center of the vertical direction. That's correct. Now let's say that I have my coordinate system, again, my x and my y coordinate system with my origin. And let's say for the case of this problem, that we already know the coordinates at this upper edge of the rectangle. So the coordinate at the top right edge of the rectangle, let's just say the coordinates are 10 in the x direction, and let's say 7 in the y direction. Furthermore, let's add that this particular rectangle has dimensions of 6 for base and 4 for height. So my question would be, what would the coordinates of the centroid of this rectangle be? Anybody have any ideas?
Let's see. I got 4, 2. The base is 6, right? So half of that is 3. Wait. No, never mind. No, I don't know.
That's all right.
7, 5.
7, 5, is that what you said?
Yeah.
Yeah. And that's correct, right? Because we know that from the origin to the top right edge of my rectangle, we have coordinates 10, 7. We know that in the x direction, we need to move half of the base, which would be half of 6, which is 3. So 10 minus 3 is 7. In the vertical direction, we need to move half of the height. So half of 4 is 2. So 7 minus 2 is 5. So we get coordinates for the centroid of this rectangle of 7 and 5. And let's look at a different but equally important example. So we've been looking at circles and rectangles, and we can agree that for circles and rectangles, the centroid is located at their center. In other words, the center from whichever direction you look at. However, how about instead we look at a triangle? So we're going to look at this right triangle. Now in this case, assuming that we are given the base of the triangle and the height of the triangle, where would this centroid be located at?
Would it be a b over 2, b over 2?
More or less. So remember from our definition of a centroid, wherever we're standing at, we will have the same volume, right, in our line of sight. Now, a triangle, it's a little bit tricky, right? Because if we were to stand at the center of these horizontal and vertical directions, we actually wouldn't have the same volume in whichever direction we look at. So for triangles, you'll notice that the location of the centroid is going to be actually at 1/3 from the big side of the triangle. So 1/3 from this horizontal edge and 1/3 from this vertical edge. And you'll notice that if you look at where your center is located, it will actually also be 1/3 from this diagonal edge. So the centroid of a triangle is going to be located at 1/3 of the distance between each edge and the altitude, okay? And for triangles, there's a bit of a rigorous proof we can do using geometry. And we're not going to do that proof in this class. Instead, we're going to come up with a method to find centroids for any type of shapes, not just circles, rectangles, and triangles, but for any irregular shape. However, if you are interested in looking at a proof for a centroid of a triangle, we can always talk about it during the review session or during office hours. Now for triangle, again, we can always have our Cartesian coordinate system with an origin. And I'll just answer this one for you. If the position of this bottom left edge of a triangle were at coordinates, let's just give it 3, 3. And if the base of this triangle were 3 and the height of this triangle were 6, then that centroid, that x and y bar location for this triangle would have to be equal to, in the x direction, we move 3 towards this point. Then we have to move 1/3 of the base. So that's 1/3 of 3, and that's 1. So the x coordinate would be 4. In the y position, we would move 3, then 1/3 of the height. So 1/3 of 6 is 2. Therefore, 3 plus 2 is 5. So my centroid for this triangle would be located at coordinates 4, 5. Okay, so that's essentially a bit of an introduction, right, to the centroid. However, in this class in statics, the geometric center, this centroid, isn't exactly what we care about. It's not the most important part of this course. The most important thing that we care about in this course is actually with relation to forces. So in order to find out about these forces, we need to define a couple of extra terms. So we said that the centroid is the geometric center of a body. The center of mass is essentially the centroid of a mass distribution of a body. Now, what do I mean by that? When I say the centroid of the mass distribution, I mean that if you were to stand on the center of mass and you were to look at in any direction in a body, your line of sight would essentially see the same amount of molecules. In other words, the same amount of mass. Now, just by a bit of intuition, you may think that centroid and center of mass should essentially be the same, but that really depends on the density of a system or the density of a body. For example, if I had a homogeneous rectangle, let's say it's a rectangular steel plate whose density is constant throughout, then I can safely say that the center of mass will be at the same location as the centroid. In other words, my centroid, which I'll call C, would be at the same location as the center of mass, which I'll just call Cm. And the reason is because since the density is constant throughout the entire plate, then wherever I see, whatever direction I see an amount of volume, I'm going to have that same amount of mass. So what I'm getting at is that if the density of a body is constant, then the center of mass and the centroid will be in the same location. Okay? However, if the density of a body is not constant, then the center of mass and the centroid will not be in the same location. So you may have seen, right, you may have realized that different materials have different densities, which means that when we combine different materials in a body, we're going to have different distributions of mass throughout the body. And when that happens, the center of mass and the centroid will not be located, right, in the same place. Now, there's a couple of interesting things about the centroid and the center of mass that we're going to learn as we work on this particular topic. However, one of the, I would say, most important things that I feel that all students should realize is that the centroid and the center of mass, they don't necessarily have to be located inside the body or within the body. So I'll give you an example. Let's say that instead of looking at a circle, let's say that we're looking at a donut, where essentially my body is composed or is located between these two concentric cylinders. Now, my question to you would be, is there any point in this body, right, where I can stand and visualize the same amount of volume no matter which direction I look at? What do you think?
No, I don't think so.
There isn't, right? Wherever you stand, you're going to have more volume on one side and less volume on the other side. So in this case, what's the centroid? Well, in this case, notice that for any object, no matter what it is, for any object, there always has to be a point where you can visualize the same amount of volume or mass in whatever direction you look at. And in this case, that point is actually going to be at the very center of the void in the body. In other words, my centroid here is actually not located on my body. It's located outside of my body. But notice that if I were to stand at a point at the center, no matter where I look, I will always visualize the same amount of volume in whatever direction I look at. So the centroid doesn't always have to be located on the body. The centroid can be located away or outside of the body. So that's one point I would like for you to take home today, because it's going to be important and it's going to clear up some confusion whenever we're solving problems. The centroid can be located outside of the body. Okay. So we've talked a little bit about some general definitions of the centroid, right? However, we also want to talk about a more mathematical, right, less physical and more mathematical definition, which is what we're going to use in this class. So in this class, I would like to find the center of mass or the centroid of an object. However, in order to find it, I'm going to have to come up with a relationship, right, between forces and moments. And in order to do that, I need to come up with a new term. I need to define a new term that relates centroid and center of mass to a force. Now, when we talk about mass, the force that's most commonly associated with mass would be our gravitational force. So I'm going to define a point called the center of gravity. And the center of gravity will essentially be the point where my gravitational force acts on. What do I mean by that? We know that the weight that you feel, if we were to reduce it to a point force, then that weight would act on one point. Now that point is what we're going to call the center of gravity. Now on Earth, the center of gravity is always going to be located at the center of mass. However, if we have different gravitational fields, varying gravitational fields, then we're going to have a varying center of gravity. However, in this class, most of our problems are going to be on Earth under standard engineering conditions, and therefore it's safe to say that the center of gravity and the center of mass will be located at the same points. So what that allows us to do is it allows us to use the center of gravity and the theory behind the center of gravity to find the center of mass of an object. So we define the center of gravity as the location of your weight, right? FW, your weight. And we know that if your gravitational field is constant, in other words, if your gravitational acceleration for the body is a constant, then the center of gravity, which we'll call capital G, will actually be equal to the center of mass. And this will be true for most problems that we will do in this class. Now, why do we need to define these terms? So we want to know what the center of gravity is because the center of gravity allows us to use the weight of an object in order to figure out where the center of mass of an object is. And what we're going to do is we're going to come up with this relationship. Okay? So to do that, we're going to have to turn to our old friend, calculus. We can always find relationships for centroid using geometry. However, a more generic approach would require us to use calculus. Okay? So what we're going to do is we're going to come up with an expression that will allow us to find the center of gravity and by extension the center of mass and the centroid for a generic, irregular, three-dimensional body. In other words, we're going to be looking at our x, y, and z coordinates. And let's say that we want to find the centroid of this three-dimensional body, whatever that might is. Now, what do we know about this body? Well, let's say that we know that this body has a mass of m. And let's say that we also know that this body occupies a volume of v. We know that this body has a weight. And we know that that weight will act on the center of gravity, which we will call g. If we set our Cartesian coordinate system where z is the vertical axis, then the weight will act along the z-axis. So that's what we know about this body. We have a mass m, a volume v, and a weight Fw that acts at point G. So now I can use differential analysis in order to find the centroid or the center of gravity of this object. So bear with me, we're going to have a bit of a long explanation, but in the end, we're going to come up with a relationship that we can use for any body in any shape. So let's start by selecting a differentially small, a tiny, really small element. Okay. Now this differentially small element, I'm just gonna draw it a little bit bigger here. This differentially small element is really, really, really small, infinitesimally small, and it's going to occupy a volume of dV, a tiny, tiny volume of dV. We also know this element has a tiny mass of dm, and we also know this element has a weight of dFW. So that's what we know. Let's say that this tiny, tiny, tiny element is located at some arbitrary coordinates, which I'll call x squiggly, y squiggly, and z squiggly. In other words, this element is located, the element, we're going to call this element dV, is located at coordinates x squiggly, y squiggly, z squiggly. So those are some arbitrary coordinates. We have a tiny element. So what do we know about this element? We know that because it's so small, we can treat it as if it were a point. And if we can treat this element as if it were a point, then we know, right, where the center of gravity of this element will be. So if the element is located at x squiggly, y squiggly, z squiggly, and we know that it's so tiny that it's almost like a point, then we know that the center of gravity of the element, I'm just going to call it G, center of gravity of the element, is located at the same coordinates, x squiggly, y squiggly, z squiggly, because it's so tiny that the center of gravity is simply at the coordinates where the element is. We don't need to look for any other relationships. That's what we know. Now, because it's so tiny, right, then we can assume that the gravitational field through this tiny element remains constant. Because if there were any variations in gravity, this element is so small that there cannot be any variations through the element because it's an infinitesimally small element. So that means that for this element, my center of gravity and my center of mass are located in the same place. What else? We also know that because this element is so small, then there cannot be any density variation throughout the element, because in order to have density variation, we need to have a finite length. But it's so tiny that the density at one point of the element should be equal to the density at any point in the element, because they're all basically at one point. It's infinitesimally small. So that means that the center of mass is also located at the same location as my centroid. So what can I get with all this information? Well, we can use a bit of differential analysis to find some information about this element and relate it to the body as a whole. So what do we know? We know that this element has a body, a volume of dV. It's the volume of this tiny, tiny, tiny element. And we know that there are an infinite number of tiny elements throughout this entire body. What that means is that if we want to find the volume of the entire body, the volume of the entire thing, then essentially we need to add up all of the tiny, tiny, tiny elements. And we know that the summation of an infinite number of terms is what we call an integral. So we get from this analysis the following relationship. We know the volume of the entire body is equal to the integral of dV, evaluated through the entire volume of the body. And I think you can get this from math, right? Integral of dx is x. Integral of dv is v. So we know this already from math. We also know, right, that the mass of the entire body m can be found by adding up all of the masses of the infinitely small elements dm's. In other words, the mass m is equal to the sum of all my elements dm, and we know that an infinite sum is an integral. So the mass of the body is equal to the integral of dm, for that infinitesimally small term. Finally, we get the relationship of the weight of the element. We know that the weight of the entire body, that's Fw, is equal to the sum of all of the tiny, tiny, tiny weights of this element dFW. And we know that an infinite sum is an integral. So we get that Fw equals integral of dFW. So that's everything we know so far for this particular element. And the reason we're doing this is because we want to now apply the relationships that we've learned, right, between forces and moments to use this information to find the location of this center of gravity, okay? So in order to do that, let's think of the following. We have our body on the X, Y, Z space. And we know that there is a weight associated with this body that acts on my center of gravity, G. So now I can tell you some things. One, I can tell you that the moment that this body exerts around the origin can be looked at as the components of the moment that this body exerts around the X or the Y axes. In other words, if I want to find the moment that this body exerts about the Y axis, that should be equal to my weight of the body multiplied by the X coordinate of the centroid. So why is that? Well, you know that in order for this force to cause a rotation about this Y axis, then we need to find the distance perpendicular to the line of action of this force from this axis. So what is that perpendicular distance? Well, because the force is already acting only in the Z direction, and that perpendicular distance will essentially be a distance along the X-axis. And that distance along the X-axis is simply the coordinates of my centroid, which I'll just call X bar. So we say that this centroid will have coordinates of X bar, Y bar, Z bar, and the distance, right? The distance between my force and my Y-axis will be simply X bar. So that's what we know about this body. But now let's figure out what we know about the differentially small, infinitesimally small elements with volume dV, with force dFW, and with mass dm. So what do we know about this element? We know that this element will exert its own tiny, tiny, tiny moment about the X, Y, Z axis. And again, the tiny moment, I'll just call it dm, in the Y direction should be equal to its weight, that's dFW, multiplied by the X coordinate of the centroid of this element. Now we already said this element is located at coordinates X squiggly, Y squiggly, Z squiggly, which means that we can multiply this weight by this coordinate. We know that this tiny, tiny, tiny element exerts a tiny, tiny, tiny moment about the y-axis, which is found by multiplying the tiny weight times the x coordinate of the centroid of this tiny element. So it's the same equation that we have above, except that this is for the whole thing, this is for the tiny thing. However, we know from calculus that the total moment that this body exerts over the y-axis should be equal to the sum of the tiny moments that this infinitesimally small element exerts. And we know that total moment can be found by multiplying the weight of the object times x bar. And we know that the sum of these tiny moments is essentially an integral. Likewise, we know that this integral is integral of the tiny moments, and these tiny moments can be found by multiplying x squiggly times dFW. I just changed the order here so that we can have our differentially small term on the end at the end of the equation. So if we look at this equation, what we have is a pretty simple equation that can be solved by simply solving for x bar. So we get that x bar should be equal to the integral we have here, the integral of x squiggly dfw divided by the total weight. And we know the total weight is simply equal to the integral of dfw, because integral of dfw is just dfw. So we get our equation for the x coordinates of the centroid of this element. And we don't have to repeat this analysis here in class for every single axis, but we'll find that if we repeat this process, we'll get that the y coordinate of the centroid would simply be the integral of y squiggly dfw over the total weight. And we'll get that the z coordinate of the centroid will simply be the integral of z squiggly dfw over integral of dfw. So these three would be the coordinates to the center of gravity. Now, we said that while in most standard engineering conditions, the center of gravity and the center of mass will be the same, and we're going to treat them as if they were the same in this class, I don't want you to go home with the idea that there's always going to be the same number. And because of that, we can come up with some relationships, right, for the center of mass. Notice that if we repeat the same process, but instead of focusing on weights, we were to focus on mass instead, we will get that the x coordinate of the center of mass will be equal to the same integral of squiggly. However, instead of evaluating over infinitesimally small weights, we will be evaluating over infinitesimally small masses. So we get what's essentially the same integral, but evaluating over mass instead of over weight. We can repeat the same process for my y coordinate, as well as for my z coordinate. And these equations essentially give me the coordinates to the center of mass. Hopefully, we may be starting to see a trend here. I hope that you are seeing this trend with me. It looks like we have coordinates to the center of gravity, coordinates to center of mass, and we can find them using the same integrals. Now, likewise, we can find coordinates to the centroid in the same way. Because we know that this element, in addition to having a small weight dfw, a small mass dm, it also has a small volume dv. So we can use that small volume dv, repeat the same analysis, and land at very similar equations. So my x coordinates would essentially be the same integral, but evaluated over the volume instead of the mass or the weight. Likewise, my y coordinates would be the same equation, evaluated over the volume. My z coordinate would be the same equation, evaluated over the volume. These equations collectively give me the coordinates to the centroid. Now we already know that there are some cases where the three will be the same, but we don't want to assume that the three are always going to be the same, which is why I'm giving you all these different coordinates. Now, these coordinates for the centroid are given to us assuming that we're looking at a three-dimensional shape. However, sometimes our problems are going to be simple enough that we can assume that they are two-dimensional shapes instead of three-dimensional. So these are for three-dimensional bodies. But then for two-dimensional bodies, if a body only exists in the x y plane and not an xyz space. So if we have a two-dimensional body in xy plane, we wouldn't really be dealing with volume because you need 3 dimensions for volume. So what do you think we would use to replace volume in 2 dimensions?
Area.
Yeah, that's correct. We would have our area. So we can repeat the same analysis, and we get that the x-coordinate would simply be integral x squiggly evaluated over the area. We can do the same for the y-coordinate. And we can do the same for the z-coordinate. And these are the coordinates for the centroid for 2D bodies. Okay? Now, what if we're only looking at a one-dimensional body? In other words, let's say we're looking at a curve. It can still be an XY space, but it is a curve. It's a one-dimensional element. One-dimensional elements do not have area. So what do you think we need to integrate over if we cannot use an area?
Is it distance?
Yeah, a length, right? A distance or a length. That's correct. So we get that the x-coordinate of the centroid will simply be the same equation, but evaluated over a length instead of over an area. The same applies to the y-coordinate. The same applies to the z-coordinate. Those for one-dimensional bodies. Now, these are a lot of equations, but hopefully you can see the pattern here, right? The coordinate will simply be equal to the integral of the squiggly term evaluated over whatever it is we're evaluating, divided by the total amount of property that we are evaluating over. So for center of gravity, we use weights. For center of mass, we use masses. And then for centroids in 3 dimensions, we use volumes. In 2 dimensions, we use areas. In 1 dimension, we use lengths. So those are our equations for calculating our centroids and our center of gravity. I'm sure that at this point, we don't really have any questions, but I will just give you a chance to ask questions just in case before we start a problem. So are there any particular questions related to this topic or related to how we found these equations?
I have one real quick. In the 2D bodies, how do you have X, Y, and Z if there's only 2 dimensions?
Right. So remember that even though, for example, you know that this is a line, it's a one-dimensional body, but we can still see it in XY space, right? Because we can use these XY coordinates to look at this line. Does that more or less make sense? So in the line, we still have XY. So likewise, we can have an area, for example, a small area that's, let's say, inclined at an angle from one of my axes, which means that this area can still exist in XYZ space. It's just you can think of it as a really, really, really flat plate existing in XYZ, in which case we still need a Z coordinate for the centroid. Okay, so if you were to look at this in 3 dimensions, you can think of this area as a very, very, very flat sheet of paper or something in 3 dimensions. So just like this paper, I can simplify it as 2-dimensional because the width is so small that it's negligible. I can still bend it, right? And it can still exist in 3 dimensions, even though we can look at it as a 2-dimensional area. That's essentially what we're doing here. Hopefully this will become a little bit more clear when we start doing problems, but I think that's about the best explanation I can give.
Yeah, thank you very much.
No problem. Okay, so let's go ahead and start our problem. Well, we still have a few minutes left, so hopefully we can use the remaining minutes to try to solve a centroid problem to see if we actually know what we're doing. And you'll notice, once we start solving these problems, you'll notice that the hard part is not calculating the centroid. The hard part is going to be setting up your integral. Because we already know these equations, but the hard part is actually going to be setting up this integral. Solving it, yeah, some of them may be hard to solve, but setting up the integral is actually what's going to take most of your juice in this problem. So what I'm going to do is I'm going to start with example 9.1 from your book. And I want to start with examples. However, if you look at the course website, I actually already have a video solving one of the fundamental problems, which is a little bit more complex than what we're going to solve today. So in example 9.1, we are given a rod. And this is an interesting example because a rod is essentially a three-dimensional body, but we're told, right, because it's a rod, because it's a very, very thin rod, we can actually look at it as if it were a one-dimensional body. So we're given this rod, and again, it's so tiny, so thin, that we can visualize it as if it were a one-dimensional body. And we're given some information about this rod. First, we're told that the rod has a shape that can be graphed as x equals y squared. If you're still confused, remember this is essentially the shape of a parabola. Right, the parabola in this direction would be y equals x squared. In this case, x equals y squared would be a parabola in this direction. We have a parabola of x equals y squared, and here's my rod. And my rod starts at my origin and ends at coordinates 1, 1. So that's all we know about the rod. It starts at the origin, it ends at 1, 1, and it has a shape of x equals y squared. Now what we have here is essentially a one-dimensional body in two-dimensional space. Hopefully this will move towards Ryan's question. A one-dimensional body in two-dimensional space. Now, because we're starting out, let's assume that the center of gravity, the centroid, and the center of mass are all in the same location. In other words, let's assume that this rod is homogeneous, so density is constant everywhere, which means that the centroid and the center of mass are in the same location. And then let's also assume that my gravitational field is constant, so that the center of gravity and the center of mass are in the same location. So given this information, I would like to find the location of the centroid of this rod. And this may be a bit of a tricky question because we have a one-dimensional body, but it's a curved one-dimensional body. If I want to find the centroid, hopefully this starts to give you some ideas. Maybe the centroid will not be located in the rod itself, but who knows? We'll see if that's the case or not. So before we start solving any of these problems, I think we need to answer ourselves the following question. Are we dealing with a length element? Are we dealing with an area element? Or are we dealing with a volume element? So what do you think? Based on this, on the description of this rod, what do you think we're dealing with? Yeah, we're dealing with a length element. Of course, we know the rod is three-dimensional. If it exists in reality, it has to be, but because it's so thin, we can treat it as a length element. So then, knowing that this is a length element, there are several steps we need in order to set up our integral. And hopefully we'll walk through these steps, and we'll see that, again, it takes a little bit of thinking, it takes a little bit of calculation, but once we know how to solve it, this will help us not just for this class, but for our future classes. So in order to set up your integral, the first thing I would like for you to do is to start the same differential analysis that I did to come up with the equation. So I'd like for you to locate a differential element. That is a very, very tiny, right, infinitely small element. Now, you can choose wherever you want that element to be. So let's just say that your element is located at an arbitrary point. My element will be located at some arbitrary point, which I'm going to call xy. It can be anything. Xy can be anywhere in the rod. I'm going to pick my differentially small element to be at this arbitrary point. And because we're treating this rod as a one-dimensional element, this differential element is essentially a point. So this differential element is located at xy. Now we know that this is a differentially small element. And we know that this is a one-dimensional rod. And because it's a one-dimensional rod, that means that this differentially small element will have dimensions of dl along the length of the rod. So those are its tiny, tiny, tiny dimensions, dl. So that's the first step. You want to locate a differential element at an arbitrary point. Hopefully this looks easy, right, for now. If it were an area, we would locate a differentially small area at an arbitrary point, but we can think about that later. So right now, let's find a tiny, tiny, tiny element at a random point, an arbitrary point along the rod. I'll call that point xy. Once you have your element, you will have to locate the coordinates to the centroid of that element. Now, when we did our differential analysis, we called those coordinates x squiggly and y squiggly. So that's what I'm going to call the coordinates again. So we're going to locate the coordinates to the center of the element, which I'll call x squiggly and y squiggly. And I'm going to express these coordinates in terms of the location of the element itself. Now this step may seem a little bit redundant or out of place for this problem because this is a one-dimensional problem, but I'd like for you to consider this step anyway, because when we look at 2 and 3 dimensions, this will be a very important step in our process. So what I'm getting at is, if this point is located at a point xy, then where do you think the centroid of this point is located at? What do you think? The point is located, this element is located at point xy. What about the centroid of this tiny element? Where is it located at? Yeah, x squiggly, y squiggly, but then how is that related to xy? Is it the same point? Is it a different point? Yeah, exactly. In this case, x squiggly and y squiggly, which are the centroid of the element, are actually x and y. They're the same points. So in other words, what I can say here, right, is that x squiggly is equal to x and y squiggly is equal to y. Now, this looks, like I said, this looks like it doesn't make much sense in this particular problem. However, the reason we have to solve this step is because when we're dealing with areas and volumes, these x squigglies and y squigglies may not be the same as x and y. But for now, we're dealing with one dimension, so let's continue to deal with one dimension. So we located a differential element. We've located the coordinates to the center of the element, so we get that x squiggly equals x, y squiggly equals y. And now, we could jump directly to expressing our integral, or to formulating our integral. However, our integral is dl, is over a length. However, we're looking at x and y space, x and y plane, which means that our next step will have to be to express the length of this element, which is dl. So we're going to express the length of the element which we know that is called dl. We're going to express it in terms of x and y. So why am I doing this? Because notice that the shape of the element is already given to you with an x and y equation, which means that when you integrate, you don't really want to integrate over dl. You want to integrate over dx or over dy, whichever one's easiest for you. So I want to express the length of this element in terms of x and in terms of y. So how do we do that? Let's look at a differential element. So if I were to blow up this differential element, essentially what I would see, right, if I were to blow it up, we have this tiny element, and this element will have a length dl, as you can see. Now notice that as the element moves at a length dl, it is actually being displaced a horizontal distance dx and a vertical distance dy. Infinitesimally small length dl essentially moves at an infinitesimally small horizontal distance dx and an infinitesimally small vertical distance dy. So given this information, how do you think we can express dl as a function of dx and dy? What do you think? Exactly, the Pythagorean theorem, right? We have what's essentially a right triangle, and because we have a right triangle, we know that dl should be equal to the square root of the sum of the squares of the two sides. In other words, dl should be equal to the square root of dx squared plus dy squared. So we have expressed our element dl in terms of x and in terms of y. However, when we set up our integral, remember our integral will be evaluated at dl. We can't really evaluate our integral, right, if we're going to have multiple differentially small elements to integrate over. So one advice that I would give you is to make sure that you will always leave a free element on the right side of your expression. In other words, and when I say free, I mean an element that is not elevated to a power. In this case, it cannot be an element inside a square root. So always leave a free element in your expression. So you can choose to leave your x or your y free. Now, because I want to solve it the easiest way, I'll just cheat and tell you it'll probably be easier to leave our dy as our free element, okay? So in this problem, we want to leave a dy that's free. So how do we do that? Well, we have our equation, dl equals square root of everything inside the square root. How do you think we can take that dy term out of the square root? Any ideas on how we can take an element out of a square root?
Just square both sides?
We could square both sides, but remember that once we apply this to the integral, we're going to have to take the square root at the integral, and then we're going to end up with the square root again. However, I like what you're saying, right? It's not entirely wrong, but maybe we can get an idea from that. Instead of squaring both sides, let me remind you of the following. What do you think is dy squared over dy squared? What is that equal to?
1.
Just 1, right? Okay. Which means that if I multiply anything by dy squared over dy squared, I'm not changing the equation, right? Because I'm just multiplying it by 1. So there will be no change to the equation. So why do I want to do this? Notice that I already have a dy squared here. So I would like to take this dy squared out of the square root, but I can't do it because I cannot factor this out. But if I can factor this dy squared out, I can take it out of the square root. So what I'm going to do is I'm going to multiply these two terms by dy squared over dy squared. That's what I'll do for this particular problem. I'm going to multiply by dy squared over dy squared, which is just the same as multiplying by 1. So what does that look like? I get dl, and I'll get the square root of, I got dx squared multiplied by dy squared over dy squared. So I'm going to write it here, dy squared over dy squared multiplied by dx squared. So far, is that making sense so far? We're multiplying dx squared by dy squared over dy squared, okay? And now I can multiply dy squared again by this term. So I get dy squared over dy squared multiplied by dy squared. So what does this leave me with? Notice that if I want to take my dy out of this square root, I need to factor it out somehow. So by multiplying everything by dy squared, can I factor out my dy now? Yeah, I can, right? Notice that I have a dy, I can factor them out. So I can say that dl will be equal to the square root of dy squared, which I'm factoring out of this entire expression. So this will be multiplied. And if I factor out dy squared, I'm left with dx squared over dy squared, right? So I'm left with dx squared over dy squared. Because both of them are squared, I can just write it down as dx over dy squared. This is the same thing. Plus, I'm factoring out dy squared here, and I'm left with dy squared over dy squared. And we know that that's just equal to 1. And will you look at that? You know that this is the same as dy times square root of this term, because we know that the product, two products inside a square root is equal to the product of the square roots, right? The square root of a product is equal to the product of the square roots. So what I can do is I can say that the square root of dy squared is just dy, and I end up with an expression for dl equal to the square root of dx over dy squared plus 1, and all of that multiplied by dy. So that took a while. It took a little bit of work, but now look, we essentially have an equation of dl with a free dy element. Now we're not done yet, right? Because we want to express it in terms of x and y, but we still have an dx term here that we might get rid of. But up to this point, does everything make sense?
So if you divide, oh wait, never mind, I got it. Never mind, I figured it out.
Nice. I answered your question without saying a word.
Yeah,
nice.
No, which is nothing. I figured it out.
Okay, no, that's good, that's good. So we still need to get rid of these terms. However, now we can use just simple calculus to get rid of the terms, right? So we know that there's a relationship between dx and dy, right? Because we know here that in this rod, which is essentially our length element L, x equals y squared. Right? So if x equals y squared, what do you think dx over dy equals? First off, what is dx over dy? What does that represent mathematically?
Derivative.
The derivative, right? The derivative of x with respect to y. And I get that x equals y squared. So what's the derivative of x with respect to y?
Y.
Yeah. So dx over dy is simply 2y. And now look at that. My equation becomes a simple equation in terms of dy only. So dl is equal to the square root of dx dy. Dx dy we already know as 2y. All this squared plus 1 multiplied by dy. And now I essentially end up with an expression for dl equal to the square root. 2y squared is simply 4y squared plus 1 dy. So I did it. I expressed my length dl in terms of x and y. In this case, I expressed it in terms of y because that's the variable that I chose. You could do this by expressing it in terms of x. However, that would have left with a harder integral to solve. And you can try yourself. If you, instead of multiplying by dy squared over dy squared, you can multiply by dx squared over dx squared and end up with an equation with dx. However, that equation is not going to be too easy to solve when it comes to the integral. Okay. So we express the length in terms of x and y. And now we can go to our final and easiest step, which is to integrate. We want to find the location of the centroid. So we know that x bar is equal to the integral of x squiggly dl over the integral of dl. Okay, so what is x squiggly? Well, we already found from step number 2 that x squiggly equals x. So I get the integral of x times dl. But then what is dl? Well, we already found from step number 3 that dl equals square root of 4y squared plus 1 dy. So I get x times square root of 4y squared plus 1 times dy. Likewise, we have the integral of dl. We know that dl is equal to this expression. Good. Of course, we need to apply limits to this integral because we're integrating over the length of this rod. It's not an infinite rod, right? It's a finite rod that starts at 0 and ends at 1, 1. Now, because we're integrating over the y direction, I want the y limits of this expression. So at the beginning, my y coordinate is 0. At the end, my y coordinate is 1. So that means that my integral will go from 0 to 1. This is number 1. We have an x variable here, but x actually varies with y. So I can't treat it as a constant. Instead, I need to replace this x with whatever relationship I get for y. So what do I have? I have that x equals y squared. Therefore, x here will equal y squared. And I get y squared integral of 4y squared plus 1 dy divided by the integral, same limits of integration from 0 to 1. So integral from 0 to 1 of square root of 4y squared plus 1 dy. And there we go. We've expressed our x coordinate of the centroid into an integral that we can solve. I'm not going to say that we can easily solve, but we can definitely solve this integral. It's very solvable. It's going to take a while. It's going to take a while for you to solve it, but it is solvable. Okay? You can try it. You can review your math. Just so that you can review, the answer for this problem will be 0.410. All the length scales are meters, so my answer will be in meters. Okay? Likewise, y direction, we get the integral of y squiggly dl over the integral of dl. Now we already know that y squiggly equals y. Therefore, I get the integral of y squiggly equals y times dl. And we know that dl is this nasty expression. And we know that the limits of integration are from 0 to 1. So I can integrate this from 0 to 1. And hopefully you'll see that the integral in the denominator is actually the same integral in the denominator of the x coordinate, so you only have to solve it once. The integral in the numerator changes a little bit. So just for your review, the answer for this question will be 0.574 meters. Now we've run out of time, so I'm not going to keep you here any further. But essentially, that is how you solve it. The hard part is setting up your integral. Once you have your integral, all you have to do is integrate. And you may need to review your math a little bit, but it's essentially setting up the integral that is the hard part in these problems. Okay.
We're allowed to use a calculator for these or no?
Yeah, you can.
Yeah.
Yeah, you can. Don't worry. All right. I will see you on Wednesday. I'm not going to keep you here any longer. So I'll see you on Wednesday, and yeah, try to practice some of the homework problems. These are going to be interesting. Okay. Take care.